All right, so I actually recorded this video once already, so I have a bunch of stuff saved, so I'm actually gonna click through what I have here, hopefully to save some time to help you out when thinking about these two free response questions that are for homework. All right, so we're given this problem where a population is modeled by a function p that satisfies this logistic differential equation. And when we're looking at a logistic differential equation, remember this is the rate of change of the population over time. As time changes, how's the population going to change? Okay, and in general, these logistic differential equations follow this model that dp dt is equal to r, where r is some factor and k is what we call the carrying capacity. Different people or different books will use different symbols. Some will use C, some will use K. So K here, but I'll switch to C later on. And then K, in this case then, this carrying capacity in our problem, K, you can see is 12. And our R, the rate, that or the factor here, I should say, that is multiplying this rate turns out to be 1/5 if we will need that later on. So how do we read this? This differential equation is this rate times the population times the quantity 1 minus the population over the carrying capacity. So in general, a population curve that follows logistic growth looks like this. It kind of is concave up for a little while and then concave down and levels off at some carrying capacity C or K or whatever we're going to call it. Okay. So in part A here, it says, hey, if the initial population is 3, what is the limit as t goes to infinity of the population? So what's going to happen to the population as time passes? Now here's the cool thing about logistic growth, that it actually doesn't matter what the initial population is. As time passes, our population will grow and then level off at whatever that carrying capacity is. So as t goes to infinity, regardless of the initial condition, population goes to the carrying capacity, which in this case, our carrying capacity, K, is 12. So we can actually write that out then, that the limit is going to be 12 if P of 0 is 3. Now what about if P of 0 is 20? That'd be above the carrying capacity. But the same thing happens. If you have a logistic curve that starts above there, it'll kind of come down and level off at our carrying capacity, regardless of the initial condition. That's true for logistic differential equations, for logistic growth, that as t goes to infinity, as time passes, that population will approach whatever that carrying capacity value is. Okay, so the limit as t approaches infinity of P of t is 12 still, even if P of 0 is 20. That is part A. You get 1 point for identifying each of those answers, okay? What about part B? Part B says that if P of 0 is 3, for what value P is the population growing the fastest? And so here's what's cool also about logistic growth. This curve here is our population growth, not the graph of the derivative, but the actual graph of P. And so for part B here, we can think, okay, if this is the graph of P, this population then is actually growing the fastest, kind of right here in the middle, right, where our population graph is the steepest. That's where the population is growing the fastest. But if we think about that, the population is growing the fastest then, right when dp dt, the rate of change, has a maximum, where the first derivative has a maximum. In other words, where our p graph changes from concave up to concave down, right there in the middle. When our graph changes from concave up to concave down, the rate of change of population is the greatest. All right? And that always happens on a logistic growth curve at half the carrying capacity. At half the carrying capacity, our population will be growing the fastest. All right, that's where dp dt has a maximum right there. Our population is growing the fastest. So all we actually need to say for part B is that the population is growing the fastest at 12 divided by 2. And it's good to show how you got this. 12 is our carrying capacity. We're going to divide it in half and at 6. You could say, if you want to here, that P equals 6, making that more clear. This is a population and not a time. That's 1 point for getting that. I would recommend writing P equals 6 here. All right, 1 point for identifying that population. So part C gets a little interesting. Part C says, hey, we got this different population. It's modeled by a function y that satisfies this separable differential equation. So notice this is not a logistic growth curve anymore because we have y, which is the population, and t, not population and population. All right? Slightly different setup, so don't stress too much. They tell us it's a separable differential equation. We want to find y of t. So in other words, we want to solve this differential equation if we know this initial condition, that y of 0, the initial population, was 3. All right, so we can set up our differential equation. It's basically what they give us, and we know it's separable. And so to solve a differential equation, we need to get y's to the left, because dy is the numerator, so get y's to the left, and t's to the right. So we can do that. We can divide by y to get to the other side, to get the y to the left. We'd have the dy that stays up at the top. We can multiply dt to the other side. Notice I've just multiplied it to the other side. I'm not doing any other adjustments. I divided by y, kept dy over there, multiplied dt to the right, and there we go. So what do we do with that? This actually might be a situation where it's easier to sort of clean up this side, so we're not dealing with parentheses. So I'm going to go ahead and distribute that 1/5 in. So 1/5 times 1 will give me 1/5. 1/5 times negative t over 12 will give me t over 60. And that dt will stay. Right? Once I have my variables separated, y's together, t's together, and now it is time for my antiderivatives. Now the antiderivative of 1 over y is the natural log of the absolute value of y. The antiderivative of 1/5 with respect to t is 1/5 t, minus the antiderivative of t is t squared, right? The antiderivative of t is t squared. And then we would need to divide by that new exponent. So divide by the new exponent. There was already 60 down there, so we multiply 60 times 2, and we'll get 120. And I'll add my plus c, all right? So I've done my antiderivatives here, okay? Now I want to solve for y. In the cases where you have a natural log on the left, it is helpful to exponentiate at the start. So I'm going to exponentiate both sides. But remember, if I exponentiate both sides, I lose the natural log. And if I want to get rid of the absolute value, I can, but I need to make sure that I do the proper thing on the right-hand side. If I'm going to lose the natural log, that's from the e, but if I'm going to lose the absolute value, I got to recognize that e to the blah plus c is the same thing as e to the blah times e to the c using our exponent properties, and e to the c is some constant. I don't know what it is, and so it can absorb my plus or minus. I can just write c in front there. E to the this plus c, same thing as e to the this times e to the c. E to the c is some constant, and it can absorb the plus or minus from the absolute value. I can now plug in my initial condition, which is 0, 3. And when I do that, I'll find that c is 3. And then I have my solution to my differential equation. There it is. All right. You get 1 point for separating your variables, 1 point for your antiderivatives, 1 point for having your plus c, you just got to have it, 1 point for using your initial condition, you just got to use it, and then 1 point for solving for y. Okay. Moving on to part D. For this function that you found in part C, what is the limit as t approaches infinity of y of t? Interesting. So basically, oh sorry, those are the points. One for separating, one for antiderivatives, one for the plus c, one for using the initial condition, and one for your final answer. All right. For question D, we want to use this thing from part C, so I'm going to leave it. And we want to figure out what is the limit as t approaches infinity of this thing I got, right? So I'll just copy it over there. What's going to happen as t approaches infinity? So this is interesting, 1/5 t, but then minus t squared. If I compare the magnitudes of these, as t goes to infinity, this minus t squared is going to way beat out this t thing, right? Something squared is huge compared to just a t, as t gets really big. So my exponent becomes actually more and more negative. The negative thing wins. My exponent gets more and more negative. So if I want to, I can actually kind of think down here that this really becomes 3e to the negative infinity. Can't write equals to because that's not an equals to thing, but I can at least write it down. And if I think about 3e to the negative infinity, because my minus t squared is going to win, it's going to be my big thing. T is going to infinity, so it's really e to the negative infinity thing, which is really 3 over e to the infinity, if I want to think that in my head. This is really what's going on. So as e goes to infinity, that means the denominator gets really big, which means this fraction will go to 0, and that means this limit goes to 0. 1 point for getting that answer, and you needed to have worked with an exponential thing. You couldn't just guess your way to this to this 0 and get that point. They made that clear that year. All right, hopefully that helps out with this question here. It's a good one. Logistic growth and separable differential equations and some limits all together. Important things for logistic growth to keep in mind are A and B. Things always end up limiting at the carrying capacity. And at half the carrying capacity is when the population is growing the fastest. It's good to have this general form written down so you can see and compare what your numbers are. All right, let's keep moving. All right, so for our second problem, we are looking at f is this function here. Let p of x be the third degree Taylor polynomial for f about x equals 0. Third degree Taylor polynomial about x equals 0. Find p of x. So what do I think to myself? Well, in part A here, I'm centering my polynomial at c equals 0. So my general formula for my terms in my Taylor polynomial will look like this. The nth derivative of f at 0 times x minus 0 to the n over n factorial. Now, to start with, as usual, I want to just find all of my f things. I can find f of 0. F of 0, I'm given f is up here. That's just sine of 5x plus pi over 4. Is sine of, oh, well, if x is 0, this just becomes sine of pi over 4. So sine of pi over 4 is just root 2 over 2. There we go. Now I'd use the 0th derivative of f. Now let me find the first derivative of f. Well, I take the derivative, the first derivative of f. The derivative of sine is cosine. I'll keep the inside, but I need to multiply by the derivative of the inside, which is 5, right? So then I'm going to plug in 0 into that. Plugging in 0 into that. I plug in 0 here, that'd be 0, cosine of pi over 4, which is root 2 over 2, times quantity 5, and there we go. Now I need the second derivative, so I kind of do this again. The second derivative of cosine is negative sine, right? Then I'll keep the inside. But then I need to multiply by the derivative of the inside. There's already a 5 there from my line before, so I keep my constant multiples, remember, but I need to multiply by the derivative of the inside again. So I'm going to end up with an extra times 5. It's kind of a weird looking 5, but there we go. So now let me plug in 0 into that. F double prime of 0 is going to give me, well, if I plug in 0 here, I get sine of pi over 4. That's root 2 over 2, but there's a negative sign. So it's going to be negative root 2 over 2 times 5, which is 25. All right, moving forward, I need the third derivative, so I take the derivative again. The derivative of sine is cosine. Derivative of sine is cosine, but there's a negative sign already there, so it's going to be negative. Derivative of sine is cosine. I'll keep the inside again. Right? And I'm going to multiply by the derivative of the inside, but there's already a 5 times 5, so I got to multiply by another 5 to multiply by the derivative of the inside this time. Then what will my third derivative be when I plug in 0? So I come back over here, I plug in 0, I'll get cosine of pi over 4, which is root 2 over 2, but there's a negative sign, so it's negative root 2 over 2 times 5 times 5 times 5, which is 125. So now I have all of my f things I need for each of my terms. X minus 0 to the n is easy to do. Over n factorial, that's easy to do. So let me write out my third degree Taylor polynomial. My polynomial then is going to be, my first term is always just this constant because it's that f of 0 times x minus 0 to the 0. X minus 0 to the n is 0 in this case. X minus 0 to the 0 over 0 factorial, so all that stuff is 1. So there we go, just leave it like that. Plus, then I need my first derivative, so I'm going to copy it down. Times x minus 0, so that's x to the first power, so that's just x. Over 1 factorial, so I'm not going to write it. Then I'm going to multiply by my next term, which will be plus this thing, but it's a negative thing there. So I'm going to say minus root 2 over 2 times 25, because that's that second derivative value, over, now I'm in my second derivative. N is now 2, so I need to put this over 2 factorial. I didn't write 1 factorial, 0 factorial, because both those were 1, so I didn't worry about that. So there we go. Over 2 factorial. So it's my second derivative I found over 2 factorial, and it needs to be times x minus 0, which is x squared, so just x squared. I'm going to rewrite this real quick, make it a little tighter, x squared. The derivative I found over n factorial times x minus 0 to the n. All right, minus, Then I use my last derivative, my third derivative here, because I need the third degree Taylor polynomial. So it's negative root 2 over 2 times 125 times x minus 0, so x cubed, because I'm in my third term, over 3 factorial. And there we go. There is my third degree Taylor polynomial. It's minus 1 point for each missing term. You will deduct only once if you make a mistake about the value of sine of root pi over 4, and only once you make an error about the the cosine of pi over 4, and only a minus 1 maximum for all extra terms you might add, or the misuse of an equal sign or something. Okay, so let's do part B. I'm going to do it in red because it's related but a little different. Part B says, find the coefficient of x to the 22 in the Taylor series for f about x equals 0. So this one we just want to kind of think ahead. Let's imagine we continued this series up until x to the 22nd power, the 22nd degree Taylor polynomial, and find. We want to know what's the coefficient of that x to the 22. So basically, the numbers here, that is not part of the x stuff. So basically, if I continued this thing, what is my term going to be? Well, it's going to be x to the 22. So let me see if I can notice a pattern. This is really a question about patterns. Notice if I want to know the numbers, the coefficient, all the other numbers besides the x to the power, that the denominator, the factorial, corresponds with the power over x. So I can at least write over 22 factorial. That's going to be there. What else do I notice? I notice that there's a square root of 2 over 2 everywhere. So I can take that. I also notice that in the n equals 1 term, I had 5 to the 1. And the n equals 2 term, my x squared term, I had 5 squared. In my n equals 3, my x cubed term, I had 5 cubed. So it looks like I also need 5 to the power of n, in which case here it's 22. To match up, notice the power of n corresponds to the power on x. So the power on 5 corresponds to the power on x. So I need that. Then the final question is, well, is it going to be positive or negative? So we got to do some thinking. If I label out my terms here, 0, 1, 2, 3, so n is 0, n is 1, n is 2, n equals 3, we can kind of notice a pattern, because if I took the derivative down here of cosine, the derivative of cosine would be negative sine. There's already a negative, so it will take me back to positive sine. It would basically take me back to the beginning here, and I would have a positive value. So basically I find out, hey, whatever my fourth derivative is would be positive. I also know that my 0th derivative is positive, my first derivative is positive, second derivative is negative, third derivative is negative, and that fourth derivative, if I took the derivative again of cosine, it gave negative cosine, sorry, would get me back to positive sine. I basically start over from here, right, at 0, my 0th derivative. In other words, my fourth derivative, sine-wise, is like my 0th derivative. Then I took the derivative of that, I'd be like my first derivative, and the pattern continues, plus, plus, minus, minus, plus, plus, minus, minus, as I take derivatives, okay? So one way you can do it is just count. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. 22 power, I'm going to be a negative sign in here. So I do know that my term is actually going to be negative. It's going to look, my coefficient is actually going to look like that. I know my term is going to be negative because that's, if I count up from 0, 1, 2, 3, just using this pattern, the 22nd term comes out to have a negative sign. So I put that, a negative value, so I put that there. And so my coefficient is just the number, so I box all that stuff. You get 1 point for the magnitude and 1 point for the sign. Okay. I really like this question. It makes you do some good thinking about how to find terms and the coefficients kind of farther down the line. If you don't like the counting thing, you can also think, hey, the pattern repeats every 4. So 0, 4, 8, 12, 16, 20. 20 is going to be positive. 22 is not a factor of 4, so it's going to be negative. All right. And if we continue here, part D, I'll do it in blue, says let g be the function defined by this integral of f of t. And I want the third degree Taylor polynomial for g about x equals 0. That sounds a lot like f, but g is just the integral of f. So let me actually just treat this like I'm taking the integral of f. I want to say approximately now, because technically g is equal to the integral of f, but I'm only going to use what I've already written as my polynomial approximation of f. So it's going to be approximately 2 because I have a finite thing. If this were an infinite serious, I could put equal to and put the infinite thing here, but I kind of just have the abbreviated form, so it's not exactly equal to. So I'm going to put approximately, and just copy down what I know. I know in the end I want the third degree Taylor polynomial for g. So I'm going to copy down what I know, and notice, that got ugly, so hold on, let me fix that. I'm actually going to stop with my t squared term. That's actually where I'm going to stop. Why? Because I want the third degree Taylor polynomial for g. And I know I will need to take an antiderivative. The antiderivative of t squared will give me a t cubed thing. That's going to be my third degree Taylor polynomial. So I'm actually just going to stop here, because when I take the antiderivative, I will get a third degree Taylor polynomial. I could have written the next term that I already have up here. That's not super useful, because when you do the antiderivative, you'll get something to the fourth, and you'll need to eliminate it later on. So I'm sort of thinking ahead and stopping here, so that when I take the antiderivative, I already have a third degree Taylor polynomial. So I'm going to take my antiderivative of everything with respect to t. Notice I kept the t's in here because x is my upper boundary of my limit of integration. So antiderivative of root 2 over 2 is root 2 over 2t, plus I'll keep root 2 over 2 times 5, and then the antiderivative of t is t squared, but then I got to divide by the new exponent, minus, I'll keep all that other stuff for now, t cubed is the antiderivative of t squared, but then I need to divide by, there was already a 2 factorial, but then if you add 1 to the exponent, you always got to divide by that new exponent when you do the antiderivative, so I'm going to divide by 3. That new exponent. And now I need to evaluate this from 0 to x. What's nice about this, though, is when I plug in x, that's easy to do. When I plug in 0, I get a bunch of zeros. So when I plug in evaluate at x minus evaluate at 0, evaluate at 0 is just 0. So all I got to do is really actually replace everything with x. So I'm going to come in here. I'm going to replace all of my t's with x's, do a little rearranging and cleaning up. Notice 2 times 2 is 4. I moved the 5 to the front. You don't have to do any cleaning up, but it can be nice and helpful. I'll leave the last term just kind of a mess there. And that is my third degree Taylor polynomial for g about x equals 0. Notice it's third degree here. That's why I stopped at my t squared term, because I knew the antiderivative would get me that third degree Taylor polynomial for g. For this one, you get 2 points for your third degree Taylor polynomial for g. And let me make sure I didn't make a mistake there. Yes, okay, cool. 2 points for the third degree Taylor polynomial for g. You get minus 1 point for each incorrect or missing term, and then minus 1 max for any extra terms you have on here, or the misuse of the inequality. All right. I guess technically, if I want to be really serious about this, sorry, I should have said misuse of the equality. This should maintain its approximately equal to sign. There we go. All right, hopefully that helps you do your grading. Good luck, and I'll talk to you later. Bye.